Okay. In continuation to my previous class, today I will elaborate the methodology dichotomous region elimination technique. This is a searching technique for solving nonlinear programming problem and unconstrained problem we are considering for solving dichotomous search. Dichotomous search is a searching technique, as I said. This is an iterative process and this is totally dependent on the region elimination strategy I have explained in the last class. Now, region elimination technique in the sense that we are having a initial interval of uncertainty and slowly we are progressing further to achieve the optimal solution, so that we will get the lesser width interval of uncertainty and we will repeat the process again and again. That is the process of iteration, and at the end we will get a very small interval of uncertainty and the middle value of that interval will be declared as the optimum point. Now, how to select, how to proceed, there are certain guidelines for this dichotomous search technique. This is a very useful technique for solving unconstrained nonlinear programming problem. Here we are considering again the few assumptions. The first assumption is that the function must be unimodal. The second is that, as I said, function must be of single variable nonlinear programming problem, and we should know the initial interval of uncertainty. That means we need to know that within the initial interval of uncertainty, function must be unimodal. There must be one maxima or one minima within that interval. There is no other. Okay, then only this methodology is working. Just look at the picture. Here the initial interval has been given a to b and the length has been just symbolized as L0. We are considering the middle point and the delta neighborhood of that, so that in the next iteration I will get two approximations of the optimal solutions. One is the x1 and another one is the x2. x1 is the point that will be delta by 2 distant from the middle value of that interval. That is why the x1 will be a plus half into L0 minus delta by 2, and similarly x2 will be in the right hand side of the middle value of the initial interval of uncertainty, and that would be delta by 2 distant. That is why the value would be a plus L0 by 2 plus delta by 2. Now, we will get these 2 points. Now, we will just see the functional values at these 4 points a, x1, x2 and b. Since there is only one mode for the function, through the region elimination process where the optimum may lie, according to that we will just eliminate a portion of the interval and we will declare a new interval as the new interval of uncertainty. Again we will repeat the process, and the process is that for this one, just let me explain you the process first, then. Now, let us consider the process. Just we are considering one minimization problem, initial interval of uncertainty a to b. How the region is being eliminated? Since we are finding out the values of f at the point a, x1, x2 and b. If we see fx1 is lesser than fx2, that means minimum should lie within a to x2. There cannot be any minimum within x2 to b. That is why we will discard the interval x2 to b. Then we will go to the next, the right hand side part you see. Then the new interval of uncertainty will be a to x2. Again we will consider the middle value of that interval. Then we will consider the 2 points, 2 new approximations for the optimal solution as x3 and x4, and that would be again the delta by 2 distance from the middle value in the right hand side in the left hand side. The beauty of this methodology is that at every iteration we will get 2 approximations together, okay, and in this way we will proceed again and again. That is why after n number of iterations we will have even number of approximations, and once when we will stop the iterative process, that is the thing you need to learn. That is why I forgot to mention the other part, that if fx1 is not lesser than fx2, that means fx1 is greater than fx2. That means the optimum cannot lie within a to x1. That is why we can discard that interval in the next iteration. Okay, and new interval of uncertainty would be x1 to b. Again we will repeat the process, we will get x3 and x4. Again we will do in this way. Let us consider one example. Here we are considering one minimization problem. Minimize 12x square minus 45x plus 50, and we are considering the initial interval of uncertainty as 1 to 4. That means the interval size is 3. Let us start the process. Okay. Now, this is 1 and this is 4. We are considering x1 as, then the middle value would be, what would be the middle value? 2.5, all right, and we will consider the delta by 2 distance from this to the middle value. That is why here we will have 1.1 approximation, here I will have another approximation. One is x1 and another one is x2. Then the x1 value would be a plus half L0 is 3 minus delta. Okay. Let us consider delta is as a very small value. All right. We are considering delta as a small value because if we consider delta as a very higher value, it may happen that we may miss the optimal solution within the range of delta. We do not want to miss it. That is why as small as we take the delta, there are two advantages. One advantage is that we won't miss at all the optimal solution, and the next advantage is that whenever we are discarding the interval, at every time we can discard delta by 2. In the previous process, if you remember, bisection method and other methods, if you remember, we are considering the half of the interval. Instead of that, we are considering better value. That is why we are not considering that delta by 2 part in the next case. And if I consider the delta is equal to 0.001, then it would be 1 plus half into 3 minus 0.001, and this value will come as 2.4995, and x2 will be 4 minus half 3 minus 0.001. Okay. Now, this value will be is equal to 2.5005. Okay. If we calculate, you can check it that these values are coming. That is why we can place 2 points here. This is my x1 and this is my x2. x1 as 2.4995 and x2 as 2.5005. You can check it without doing the calculation, even you can find it out, because if you just take delta by 2 in one side, then it would be 0.0005. 2.5 minus that, 2.5 plus that, you can get these two values. That is why let us consider the functional value at 1, functional value at x1, functional value at x2 and functional value at 4. Okay, what we will see, the functional values are coming like this. This is 17, this is 12.4925, this is the value 12.5075 and 62. What the pattern you are getting, you know, there is only one minimum within the interval. Just to see, the value is decreasing and then increasing again from here to here. That is why we are sure that optimum cannot lie within these 2 points from x2 to 4. That is why we will discard this interval. All right. In the next, we will consider the interval of uncertainty as 1 to x2. My x1 is there, all right, 1 to x2, and what will be the size of this interval of uncertainty? 5, exactly. That previously the interval uncertainty I was naming L0 as is equal to 3. Now you see we are discarding a portion, that is why we are getting L2 as 1.5005. Okay. Again let us consider the middle value. Again just you take the delta by 2 distant from here, we will find out x3 and x4, all right. Then what will be your x3? x3 will be is equal to 1 plus half L2 plus delta, that is why it is coming as 1 plus half, it is not plus delta minus delta, 1.5005 minus 0.001, and this value is coming as 1.74975. Okay, and x4 is coming as x2 minus, what is your x2? 2.5005 minus half minus 1.5005 minus 0.001, and this value is coming as 1.75075. All right. Then we will get x3 and x4. Again we will find out the functional value at 1, functional value at x3, functional value at x4, functional value at x2. We know this value, this is 17, this is from the previous case, this is 12.5075, and x3 and x4 values are coming 800,751 and 7.997757. As many number of digits you can take, you will get the accurate result. Okay. Now, if we again see the trend, what we see that 17, then 8, again it is coming to 7.9, then 12. That is why minimum cannot lie in this portion. Okay. Let us discard it again. You see we are getting another interval of uncertainty which is equal to x3 to x2, because we are discarding this interval, all right, x3 to x4. That is why we are getting this one as the new interval of uncertainty L4 is equal to, if you calculate we can get it, it is L2 minus delta by 2, all right, because this is the whole L2 and L2 by 2, L2 by 2 delta by L2 by 2 plus delta by 2. This is a new interval of uncertainty, all right. Now, this value if we just find it out, this value is coming as 0.75075. We will take again the middle value, again we will consider we considered x4, x5, now we will consider x5 and x6. Let us just give you the values for your understanding, then I will show you the further iteration through the projection, because I have calculated further iteration, I calculated as good as we can get. Just you have a look of it. This is the functional value. $566,255 and this is 12.5075. Again you look at the pattern. the value is increasing, then almost same, but it is increasing and increasing more. That is why you are sure that optimum cannot lie within this region x 6 to this. Alright. That is why we are considering the next interval of uncertainty as L 6, which is equal to L 4 by 2 plus delta by 2. Okay. This way we will proceed. Just you see the tables. This is my first value I was showing you, x 1 and x 2, and if you just see, we were discarding the interval from x 2 to x 4. Okay. That is why my new interval of uncertainty was coming as from x 3 to x 2. Alright. And the upper portion I cancelled, we proceeded further and we were getting x 5 and x 6. In this way we are proceeding. Okay. Now, one thing just I would like to mention here, just to see we are getting a nice pattern. How long shall I proceed? That is the question for us. If it is given to you that find the minimum I have calculated few, just you see, I will just show you all the steps. Okay. But if it is given that find the minimum within 10% of exact value. Okay. What does it mean? It means that whenever we are getting the final interval of uncertainty, that means I am going L 2 to L 4, L 4 to L 6, L 6 to L 8. Why we are just naming the intervals as L 2, L 4, L 6? Because when I am reaching to L 2, I have already found 2 experiments. We did 2 experiments. We were getting 2 approximations for the optimal solution. When we are reaching to L 4, we were getting 4. We did 4 experiments. L 6 means 6 experiments. Okay. If I just show you the previous thing, then you can see. Just you see, while we were reaching to L 2, we did 2 experiments. While we are reaching to L 4, we did 4 experiments. While we are reaching to L 6, we reached to 6 experiments. Alright. That is why this L value is jumping to taking 2 at a time, because at each iteration 2 approximation, at each iteration 2 approximation. If I ask you what should be the interval of uncertainty after 10 number of experiments, after 12 number of experiments, can you guess it? Okay, there is a nice process to find out that thing, and that will give you another idea how to get the 10% exact value. That means, whatever exact value we are trying to get, the right hand side we will have the 10% of that, in the left hand side we will have the 10% of that. That is why we are guessing an approximation with a known approximation. It may happen, I want to get the 5% of exact value. That means, in one side 5% interval I will get, in another side I will get 5%. That means, altogether final interval for uncertainty which will contain the optimal solution will have 10% of that. Okay. 10% of what? 10% of L naught, the initial interval of uncertainty. For reaching to this exact value concept, I will show you I am giving you the answer as I told you, that what will be the interval of size of the interval of uncertainty after doing the 10 experiments, after getting the 10 approximation. That part I am going to tell you first, then I will give you the answer for this. What is my L 2? L 2 was half L naught by delta, because it was L naught by 2 plus delta by 2. Alright. What is my L 4? half L2 plus delta. That means it was half alright. Just I am substituting the value of L2 here, which I got it from the previous one. Now, if I just do it, we are getting L0 by 2 square, okay, plus here I am getting 1 by 4 delta by 2 plus half, that means it is coming 3 by 4 delta by 2 delta 3 by 4 delta. That can be written as, actually why I am doing this simplification, because I will get a nice pattern from here. I can write it 1 minus 1 by 2 square delta, alright. Going further, L6 half L4 plus delta, this is equal to half L0 by 2 square plus 1 minus 2 square delta plus delta, alright. If I just do it, I will get L0 by 2 cube, and here I will get plus, just do the calculation, you will get 1 by 2 cube delta, okay. Just to see, we are getting a nice pattern here. We are getting, this can be written as 4 by 2, this can be written as 4 by 2, this is 3 is nothing but 6 by 2, this 3 is 6 by 2, okay. That is why straight away we can say, after doing the 8th experiment, I will get L0 divided by 2 to the power 8 by 2 plus 1 minus 2 to the power 8 by 2 delta, okay. So, after doing the nth experiment, my interval of uncertainty would be where L is even, n cannot be odd, because at each time, each experiment, we are getting 2 points at a time. It would be L0 divided by 2 to the power n by 2 plus 1 minus 2 to the power n by 2 delta. That is why, if I tell you that what would be the interval of uncertainty after doing the 10 experiments, just you substitute the value n is equal to 10. If I want for 12, I will get it 12. But why we are doing so? What is the advantage of getting it? There is one advantage, because as I was saying that I want to get the 10% accuracy of the exact value. One side 10%, another side 10% accuracy. That means, it means that final interval of uncertainty divided by L0, because we are saying that L0 is the 100% for me initial. We want to get the accuracy over L0, okay, and the half of it, because 1%, this must be 10 by 100, alright. If I just do the calculation, what I am getting, you see, L0, that means 1 by 2 to the power n by 2, L0 will cancel, okay, plus 1 minus 2 to the power n by 2 delta by L0 is less than 1 by 5, that means 0.2, okay. For the given example, we were having L0 is equal to 3. No, 2 is there, na? That is why it is coming to 0.2. Now, L naught is 3, it was there in my example. Not only that, we were considering delta is equal to 0.001. That is why if I just substitute here, I want to find out how many experiments I have to do beforehand, because I will stop my iteration there itself. Just you see, I will put 2 to the power n by 2 plus 1 minus 2 to the power n by 2, 0.001 divided by 3 less than 0.2, or 1 by 2 to the power n by 2 if I just take common, then 1 minus 0.001 by 3 is less than 0.2 minus 0.001 by 3. Am I right? Because I have just considered 1 by 2 to the power n by 2 common, I took common from here and this is going there. Okay? If I just do it, I will get 2 to the power n by 2 into, just do the calculation, you can get it for 999,667 less than 0.1996667, and from here we are getting 2 to the power n by 2 is greater than 5.000678. Then can you tell me what should be the value for n from here? I can do it by taking log both sides, but here since the number of experiments are very less, it is not that 100 number of experiments I need to do. If I have to do, then I will do that logarithm of both sides, I will get the value for n. But here if I consider n is equal to Cx, then it will be just, because n equal to 2, if I consider it will be 4, cannot be greater than 5. The next, the minimum value of n is equal to 6. That is why I have to do 6 number of experiments. And whatever I did here, I need not to do so many things together. I have to just stop here itself. Just I am showing you, I was getting the better approximations, but I need not to do, because I can stop it here. I can say that x7 to x8, that should be the final, not really, x3 to x6 is the final interval of uncertainty. Alright. After doing the 6th experiment, sorry, I will say 1.74975 to 1.938 should be the final interval of uncertainty. Okay? Take the middle value of that, you can get the solution. But what is the exact value of this function, that very easily you can find out through the classical optimization technique. What was my function? My function was x to the power 12x square, that means 20, if I just take the first order derivative, it is coming 24x is equal to 45 by equating to 0. That is why x I will get from there. We can cross check whether my calculation is proper or not. Okay. Thank you for today. Next class I will tell you how to solve, how to have another very nice method, a searching technique, that is called the Fibonacci method, how to get the optimal solution through that only. Okay. Thank you.